The photoelectric effect is the observation that many metals emit electrons when light shines upon them. Electrons emitted in this manner can be called photoelectrons. The phenomenon is commonly studied in electronic physics, as well as in fields of chemistry, such as quantum chemistry or electrochemistry. According to classical electromagnetic theory, this effect can be attributed to the transfer of energy from the light to an electron in the metal. From this perspective, an alteration in either the intensity or wavelength of light would induce changes in the rate of emission of electrons from the metal. Furthermore, according to this theory, a sufficiently dim light would be expected to show a time lag between the initial shining of its light and the subsequent emission of an electron. However, the experimental results did not correlate with either of the two predictions made by classical theory. Instead, electrons are only dislodged by the impingement of photons when those photons reach or exceed a threshold frequency. Below that threshold, no electrons are emitted from the metal regardless of the light intensity or the length of time of exposure to the light. To make sense of the fact that light can eject electrons even if its intensity is low, Albert Einstein proposed that a beam of light is not a wave propagating through space, but rather a collection of discrete wave packets, each with energy hf. This shed light on Max Planck's previous discovery of the Planck relation linking energy and frequency as arising from quantization of energy. The factor h is known as the Planck constant. In 1887, Heinrich Hertz discovered that electrodes illuminated with ultraviolet light create electric sparks more easily. In 1905, Albert Einstein published a paper that explained experimental data from the photoelectric effect as the result of light energy being carried in discrete quantized packets. This discovery led to the quantum revolution. In 1914, Robert Millikan's experiment confirmed Einstein's law on photoelectric effect. Einstein was awarded the Nobel Prize in 1921 for his discovery of the law of the photoelectric effect, and Millikan was awarded the Nobel Prize in 1923 for his work on the elementary charge of electricity and on the photoelectric effect. The photoelectric effect requires photons with energies from a few electron volts to over 1 MeV in elements with a high atomic number. Study of the photoelectric effect led to important steps in understanding the quantum nature of light and electrons and influenced the formation of the concept of wave-particle duality. Other phenomena where light affects the movement of electric charges include the photoconductive effect, the photovoltaic effect, and the photoelectrochemical effect. Emission mechanism. The photons of a light beam have a characteristic energy proportional to the frequency of the light. In the photoemission process, if an electron within some material absorbs the energy of one photon and acquires more energy than the work function of the material, it is ejected. If the photon energy is too low, the electron is unable to escape the material. Since an increase in the intensity of low-frequency light will only increase the number of low-energy photons sent over a given interval of time, this change in intensity will not create any single photon with enough energy to dislodge an electron. Thus, the energy of the emitted electrons does not depend on the intensity of the incoming light, but only on the energy of the individual photons. It is an interaction between the incident photon and the outermost electrons. Electrons can absorb energy from photons when irradiated, but they usually follow an all-or-nothing principle. All of the energy from one photon must be absorbed and used to liberate one electron from atomic binding, or else the energy is re-emitted. If the photon energy is absorbed, some of the energy liberates the electron from the atom, and the rest contributes to the electron's kinetic energy as a free particle. Experimental observations of photoelectric emission. The theory of the photoelectric effect must explain the experimental observations of the emission of electrons from an illuminated metal surface. For a given metal, there exists a certain minimum frequency of incident radiation below which no photoelectrons are emitted. This frequency is called the threshold frequency. Increasing the frequency of the incident beam, keeping the number of incident photons fixed, increases the maximum kinetic energy of the photoelectrons emitted. Thus the stopping voltage increases. The number of electrons also changes because the probability that each photon results in an emitted electron is a function of photon energy. If the intensity of the incident radiation of a given frequency is increased, there is no effect on the kinetic energy of each photoelectron. Above the threshold frequency, the maximum kinetic energy of the emitted photoelectron depends on the frequency of the incident light, but is independent of the intensity of the incident light so long as the latter is not too high. For a given metal and frequency of incident radiation, the rate at which photoelectrons are ejected is directly proportional to the intensity of the incident light. An increase in the intensity of the incident beam increases the magnitude of the photoelectric current. Although the stopping voltage remains the same, the time lag between the incidence of radiation and the emission of a photoelectron is very small, less than 10⁻⁹ seconds. The direction of distribution of emitted electrons peaks in the direction of polarization of the incident light, if it is linearly polarized. Mathematical description: the maximum kinetic energy of an ejected electron is given by where is the Planck constant and is the frequency of the incident photon. The term is the work function, which gives the minimum energy required to remove a delocalized electron from the surface of the metal. The work function satisfies where is the threshold frequency for the metal. The maximum kinetic energy of an ejected electron is then kinetic energy is positive, so we must have for the photoelectric effect to occur. Stopping potential: the relation between current and applied voltage illustrates the nature of the photoelectric effect. For discussion, a light source illuminates a plate P, and another plate electrode Q collects any emitted electrons. We vary the potential between P and Q and measure the current flowing in the external circuit between the two plates. If the frequency and the intensity of the incident radiation are fixed, the photoelectric current increases gradually with an increase in the positive potential on the collector electrode until all the photoelectrons emitted are collected. The photoelectric current attains a saturation value and does not increase further for any increase in the positive potential. The saturation current increases with the increase of the light intensity. It also increases with greater frequencies due to a greater probability of electron emission when collisions happen with higher energy photons. If we apply a negative potential to the collector plate Q with respect to the plate P and gradually increase it, the photoelectric current decreases, becoming zero at a certain negative potential. The negative potential on the collector at which the photoelectric current becomes zero is called the stopping potential or cutoff potential I. For a given frequency of incident radiation, the stopping potential is independent of its intensity. E. For a given frequency of incident radiation, the stopping potential is determined by the maximum kinetic energy of the photoelectrons that are emitted. If QE is the charge on the electron and is the stopping potential, then the work done by the retarding potential in stopping the electron is. So we see that the stopping voltage varies linearly with frequency of light but depends on the type of material. For any particular material, there is a threshold frequency that must be exceeded, independent of light intensity, to observe any electron emission. Three-step model in the X-ray regime. The photoelectric effect in crystalline material is often decomposed into three steps. In a photoelectric effect, the hole left behind can give rise to Auger effect, which is visible even when the electron does not leave the material. In molecular solids, phonons are excited in this step and may be visible as lines in the final electron energy. The inner photo effect has to be dipole allowed. The transition rules for atoms translate via the tight binding model onto the crystal. They are similar in geometry to plasma oscillations in that they have to be transversal. Ballistic transport of half of the electrons to the surface. Some electrons are scattered. Electrons escape from the material at the surface. In the three-step model, an electron can take multiple paths through these three steps. All paths can interfere in the sense of the path integral formulation. For surface states and molecules, the three-step model does still make some sense, as even most atoms have multiple electrons which can scatter the one electron leaving.